So we have defined plain embedding, embedding of a planar graph, and then that give you this plane graph, which is a planar graph comes with embedding on the surface. So here embedding was the way to draw a graph without any crossing of the edges. And then we define the faces as the maximal region that you get from this drawing, this embedding. This embedding of a graph partitioned the plane into open sets, and those maximal open sets were the faces. Then we now want to study about this faces. So for plane graph, we have vertices, edges, and faces. And now we want to discuss about this face. And before, how do we use graph? So when we are interested in certain problem, and there are some objects that we are interested in, and then there are pair of relation, then we encode the object as the vertices, and then encode the relation as edges. And then we study this graph. So that's how we are doing. Now, these faces are our object of interest. And so for graph G, we have vertices and edges and faces. Then it's natural to ask that for given graph G, plane graph G, which have vertices, edges, and faces, can we consider another graph that has these faces as its vertices? So that's very natural idea. And then that gives rise to the following definition of the dual. The dual graph, and we write that G star of a plane multigraph G is another plane multigraph with vertices or corresponds to the faces of this plane multigraph G, and those edges correspond to the edges of G. So roughly what we want to do is the following. So the drawing is not so well drawn. Let's say this is your drawing. What you do is for each face, you draw a new vertex. This vertex corresponds to the face. So the outside face corresponds to here, and then this here, and this here. And whenever two faces share a boundary, you add an edge, which crosses this edge. So this new green edge crosses this old black edge. This new graph is the dual. Its vertices correspond to the faces in the original graph. And here the edge E star in this dual corresponds to E, let's say the HE that corresponds to E joins the vertices which corresponds to corresponding to the basis of G whose boundary contains E. So this space and this space contains the boundary and contains this HE as its boundary. So you draw. So this dual G star is a plane multigraph. So we want to specify its embedding. The plane multigraph comes with the embedding. The embedding of G star puts the dual vertex X or its base F of G in the interior of X. And for each appearance of an HE in the boundary of this space X, there is a curve within X from X to 1 point on E. So from here you draw this to 1 point. From here you draw on the same point so that you connect. Then that's the next one. One point on E, and these curves are non-crossing, and the curve to E meets another from the other side of E at the same point on E. So from the dual H E star. So with this star is a plane multigraph, and its face of G contains one vertex of G star, and its edge of G star in this embedding crosses the corresponding edge in G, and no other edges. This green one only crosses this one black edge and no other black edge, and also no other green edge as well, because this is a plane graph. So with this definition, so this dual graph is well defined. And what can it, one can check that the G star. So as this is a dual, this is defined for plane multigraph, and its dual is plane multigraph. You can consider the dual's dual. And this is same with G, if and only if G is connected. And it's not difficult to check this, so I will left this to as an exercise to you. And it's easy to see that if it is not connected, then this doesn't work. For example, in this case, what's its dual? This is the dual graph. And if you consider this dual graph, and then consider its dual, you have a different graph. So this graph is not same with this graph. Okay. And also, you can check that for so with this now in this dual, now faces become the vertex. And what are the degree of vertex in this dual graph? What is it? And so here, this vertex, okay, let's say, okay, each vertex has what? Degree 1, 2, 3, 4, 5, which is same as the number of edges on this boundary, right? And this vertex has degree 4, which is the number of edges on this boundary. So it's related to the number of edges in this boundary. And then what's the boundary? And we know that it's easy to check that for connected graph, the boundary of each face is the closed walk. For disconnected graph, it's union of, closed walk. But for connected graph, it's easy to check that the boundary of each face is a closed walk. And we define the length of a face. The length of a face in a plane multigraph. G is the total length of the closed walk in G, which forms the boundary of the face, the bounding the face. And for any case, it's a boundary of its space is different union of closed walk. So we define this length, and this actually corresponds to the degree of the corresponding vertex in dual. Then now we can find some relationship between the lengths and the number of edges. So if L of F denote the length of the face F in a plane multigraph G, and the number of edges in G times 2 is same as the sum of the overall lengths of the faces. Then what? This is same as the in dual graph. You apply handshake lemma. So I will not prove this. It's immediate because this length becomes degree there. And then in dual and then the original, you have the same number of edges. 2 times the number of edges is same as the sum of the degrees in the dual. That provides this. Okay, so we have defined this dual. And one natural question. So previously, in the previous lecture, we showed that the cycle, in Jordan curve theorem, the simple closed curve partition the plane into two parts, inside and outside, and that give you this definition of the basis. Because once you have graph, then that partitions the plane into faces. I guess cycle was the small, essential reason why faces arise. The graph has many cycles, and then those partition the plane. And in dual, what does it correspond to? What does cycle correspond to in its dual? And the following definition is the answer, and we call that a minimal edge cut is called a bond. But the bond is a set of edges which is minimal set of edges which is a minimal set of edges which disconnect the graph. So Jordan curve theorem states that a cycle cut its interior and then exterior and those interior and exterior correspond to the vertices in the dual. So intuitively, cycle partitions the faces, outside faces and inside faces of this cycle. So in dual, it's disconnecting the vertices. So you might see that this bond and cycle are dual. Intuitively, you get that intuition, right? So actually, yeah, we can show that in plane multigraph, the duality between curves and cuts, we have this duality, and then that, if you translate into the graph, then you have a duality between cycle and bonds. So that's it in plane multigraph. G form a cycle in G if and only if the corresponding dual edges form a bond in G star. So we can prove this. So consider a set D of edges in G in this plane multigraph. If D contains no cycle, then this D includes no region. Yeah, because we know that the boundary of faces are, crosswalk. So in this case, we can reach the unbounded face of G from anywhere without crossing this D. As G minus D, D star minus D star is connected. and this D star contains no edge cut. Okay, so if D is the edge state of a cycle, so what does this show? Yeah, it shows that so if this is not contains no cycle, then it contains no edge cut. So now what? If this is the edge set of a cycle in G, then the corresponding edge set, this star of the dual, is consists of all dual edges. Showing spaces inside D and say 2 the bases outside D. And Jordan-Cobb's theorem implies that there are at least one such basis, one base of each type. Thus, this D star is an edge cut. And moreover, we also conclude that if this D properly contains a cycle, then this D star also properly contains an edge cut. So, this shows that this star is minimal edge cut. You can only see the cycle. Okay. So yeah, we have introduced the concept of dual. And yeah, in the next video, we will consider what we can do with these bases. One of the useful property that we can prove for planar graph are the Euler formula, which is the relationship between the number of vertices and number of edges and the number of bases. And yeah, we will learn about that in the next video.